Hey guys, how's it going? So today we're going to talk about the pentose phosphate pathway as well as just some sugar metabolism. Now we're going to start off we're going to have this in our concept map as well, the first 6 reactions of glycolysis, because those are relevant to what we're doing with our sugar metabolism. So we're going to start off, first off we're going to look at, before we get into the pentose phosphate pathway, we're going to look at galactose and fructose. So we'll start off with galactose. We're going to show how that gets metabolized. First off, you got your galactose, and the first enzyme of the reaction is going to be galactokinase. Surprise, surprise, it's going to throw a phosphate on there from ATP, leaving an ADP, and the product galactose 1-phosphate. Go ahead and note here that if you're deficient in your galactokinase enzyme, it's due to a condition. It can be due to a condition called non-classical galactosemia, and so if that enzyme is deficient, you're going to have an excess of galactose built up. So with our galactose 1-phosphate, the next enzyme that's going to be acted on is galactose 1-phosphate uridylyl transferase. Yes, there is that extra YL. It's not uridyl transferase, it's uridylyl transferase. What that is going to do, it's going to also turn a UDP glucose into a UDP galactose. So, and those two can go back and forth because the enzyme epimerase. The product of that reaction is going to be a glucose 1-phosphate G1P. And then to go ahead and note here that if you have classical galactosemia, you're going to have a deficiency in your galactose 1-phosphate uridylyl transferase, and then you'll have an accumulation of galactose 1-phosphate. And then I believe if you've got an accumulation of that, you'll start seeing galactose backed up as well. I believe the galactose will show up in blood and urine, but I don't remember for sure. It might have been the galactose 1-phosphate. Anyway, so we've got our glucose 1-phosphate. And what that can do is that enzyme phosphoglucomutase can turn that into glucose 6-phosphate, which was one of the first product of the first reaction of glycolysis. So it can do glycolysis, or if you're in the liver and you need to make more glucose, obviously it can go the other way and use glucose 6-phosphatase to dephosphorylate the substrate. It'll kick off an inorganic phosphate and leave us with glucose. Next off, we're going to talk about fructose. Now, normally you can get that in your diet. However, there's also this polyol pathway to make fructose from glucose. You're going to find that in your seminal vesicles, so your testicles. Glucose, since glucose and fructose are just isomers of each other, I believe it's just going to move around some of the OH groups. So aldolase reductase is going to take electrons from NADPH and transfer them to our substrate. It's going to leave us with an NADP+, and sorbitol. And seeing how we've just reduced our substrate, we are going to now oxidize it right back. So sorbitol dehydrogenase is going to contribute electrons to NAD+, making it an NADH, and that'll give us our D-fructose. Now for fructose, the first enzyme of the reaction, see a theme here. What do we like to do to sugar? Phosphorylate it. So we're going to transfer a phosphate from ATP, which will make it ADP, and then that gives us fructose 1-phosphate. Now aldolase B, remember aldolase back in glycolysis, it cleaved our substrate. Well, it's going to do the same thing here. However, with glycolysis, we had 2 phosphates. We had a phosphate at carbon 1 and at carbon 6. We only have a phosphate in carbon 1 of fructose, so that is going to become our DHAP, dihydroxyacetone phosphate, which, again, as you can see here, is part of glycolysis. And then the other product from the reaction with aldolase B is going to be glyceraldehyde. So we can phosphorylate that with triose kinase, triose, 3 sugars. That's going to take a phosphate from ATP, giving ADP, and that's going to produce glyceraldehyde 3-phosphate. So, and then that can go ahead and proceed with glycolysis. So now we've talked about the metabolism of galactose and fructose. We can move on to the pentose phosphate pathway. So here we see it. It's going to start off using G6P that was produced in glycolysis. Now, instead of just going down through glycolysis, the G6P is going to be shunted off this way. That's why another name for the pentose phosphate pathway is the hexose monophosphate shunt, or HMP shunt. I believe I'm saying that right. So the first enzyme here is glucose 6-phosphate dehydrogenase. We're going to reduce an NAD plus to an NADPH. Now the whole point of this pentose phosphate pathway, well, the biggest thing we're trying to accomplish is to make these NADPHs. Now these coenzymes are used as antioxidants and can prevent or used in defense against attacks by reactive oxygen species, such as your superoxide. And so it'll defend against free radicals. So the first reaction, that's going to give us our substrate with the longest name, 6-phosphogluconodelta-lactone. That is going to be acted on by glucolactonase. It's going to add in a water, kick off an H+. So it's basically going to remove the lactone to give us 6-phosphogluconate. And we've got another reaction here where we're going to oxidize our substrate. We're going to reduce an NADP+ to an NADPH. We're also going to kick off a CO2 here. That's important because we did have a 6-carbon sugar, so we're kicking off the CO2 is going to give us ribulose 5-phosphate, which is a 5-carbon sugar. Now for the rest, those were the oxidative steps of the pathway. Everything else going on here from run out is non-oxidative. So, and when we think of this pathway, we like to think of it as using 3 G6P molecules to start, or 3 moles, however you want to look at it, because that's going to enable us to go down each of these 3 routes here. And so we also look at it as having created 6 NADPH pluses and NADPHs and 3 CO2s before we got here. So there's 2 enzymes we're going to use here. Ribulose 5-phosphate is going to interact with isomerase to make a ribose 5-phosphate, or it's going to interact with epimerase to make a xylulose 5-phosphate. Those 2 epimerases it's the same enzyme. It's just shown here for the sake of how the reactions are going to go. Now, for the non-oxidative state, there's a few rules, well, 4 of them that we really want to remember, that if you don't remember what your product or your substrate is going to be or what enzyme is going to be used, this will help. So first off, your xylulose 5-phosphate is always the reaction, or the enzyme it uses is always going to be your transketolase and thiamine pyrophosphate, always. And that reaction is always going to produce a glyceraldehyde 3-phosphate. Okay, easy enough. Another thing to remember is all the sugars that we're going to be making here, they all have a phosphate on them, and the phosphate is always going to be attached to the carbon with the highest number. So xylulose 5-phosphate, you just remember it's a 5-carbon sugar because the phosphate's on position 5. Looking ahead, the glyceraldehyde 3-phosphate, it's a 3-carbon sugar. The phosphate is on carbon 3. Now the last thing that we'll want to remember about this pathway is, since we're not gaining or losing CO2 once we get in here, the number of carbons that come out of the reaction are going to be equal to the number of carbons that go into the reaction. So the xylulose 5-phosphate, we said it's always going to produce a glyceraldehyde 3-phosphate. So it's the other product in the reaction is going to have 7 carbons, because we see the ribose 5, the xylulose 5, there's 10 there. The reactants equal 10. The products are going to have to equal 10. Okay, so let's go back to, we've made our 2 xylulose 5-phosphates and our ribose 5-phosphate. The ribose 5-phosphate, as you can imagine, can be used for nucleotide biosynthesis, because it's a 5-carbon sugar that also has a phosphate attached, which can be useful in making our backbone. So we're going to start off, look at the top here. Xylulose 5-phosphate and ribose 5-phosphate interacts with transketolase and thiamine pyrophosphate. I said that's always going to make a glyceraldehyde 3-phosphate. So we had 10 carbons coming in. The other product has to have 7 carbons. That's going to be our acetoheptulose 7-phosphate. Next reaction, we're just going to use those same products are now going to become reactants, and the enzyme is going to be transaldolase. That's going to make a fructose 6-phosphate. And so since we had 10 carbons, the other product has to have 4. That's our erythrose 4-phosphate. Now, fructose 7-phosphate, fructose 6-phosphate, if it sounds familiar, it's because, yes, we've seen it before in glycolysis, and that's where that can go. So our erythrose 4-phosphate is going to go back to interact with our xylulose 5-phosphate. Our xylulose 5-phosphate is always going to use transketolase and thiamine pyrophosphate it's always going to give us a G3P, I'm sorry, it's glyceraldehyde 3-phosphate. So this time we only had 9 carbons because the erythrose 4-phosphate only had 4. So the other product has to have 6. That's going to be another fructose 6-phosphate. Glyceraldehyde 3-phosphate is just going to go in where it can be used for glycolysis. I guess you could also use it for gluconeogenesis if you wanted to go the other way and you were in the liver. And these fructose 6-phosphates are going to go back in here. And now it's important to note that if you need to make more NADPH, you can, the fructose 6-phosphate you're making here can just go the gluconeogenesis route and use phosphoglucose isomerase to go back to G6P and then re-enter the pentose phosphate pathway again and do the whole thing all over again. That's sugar metabolism in a nutshell. Hope you guys enjoyed, and I'll see you later.